This is an introduction to translation surfaces of infinite type. And the main reference is Infinite Translation in the Wild by Vincent Delacroix, Pascal Hubert, and Ferran Valdez. And I'll put a link in the description for that. So the first thing to ask ourselves is, what is a translation surface? A translation surface is a surface with a metric that we can construct with the following recipe. We start with a countable set of finite Euclidean polygons. So here's an example. I have one rectangle, and then I have a countably infinite set of pairs of rectangles. And they all have the same width, but every pair has half the height of the previous pair of rectangles. So you can see there's the first one, and then after that we have two that are half the height, and then half the height of that, and so on. And there's a few extra vertices, which I'm highlighting here. And we're going to glue these together. So every edge is identified to exactly one other edge that is parallel and of equal length and identified by translation. So here's what I mean by that. I'm going to start gluing these together by translation. See, and I'm attaching edges that are equal length, parallel, and you can see that as I'm gluing, all I'm doing is translating the polygons. I'm never rotating or doing any other type of transformation to glue them. Okay, and this continues like this for the countably infinitely many polygons. And I'm going to identify these two edges. You see there's a number of edges that I haven't said how to identify, so I'm adding those now. And again, it's pairs of parallel edges identified by translation, and they have equal length. Okay, and now we're doing the vertical ones here, so we're going to identify this to this, and this to this, and so on and so forth. And what this means, if I start on the surface and I'm traveling like this, this is how I would continue my travel. Okay, this is just some walk that you could do around your surface. And let's see what it means near the vertices. Let's look at a neighborhood of this vertex. For example, let's just go for a walk around the vertex in this counterclockwise direction. So we see we pop out over here, and then over here, and then over here. And so actually all four of those vertices are the same vertex in the surface. And we see that a neighborhood of that vertex is isometric to a Euclidean disk. The total angle that we swept out was 2 pi. But if I look at this other vertex here, look at that, the total angle I sweep out is much bigger than 2 pi. All those vertices are actually the same in our surface, and the angle I sweep out is 6 pi. So the neighborhood is still topologically a disk, but the angle is excess, and so we call it a cone point. All right, whereas the first one is not a cone point because its neighborhood was isometric to a Euclidean disk. All right, let's look at another example of how you might glue together infinitely many finite Euclidean polygons in this way. So imagine I have these squares glued together in this way, and it continues like this, like I've shown. And horizontal edges that are vertically aligned are identified together, and vertical edges that are horizontally aligned are identified together. And let's take a look at one of these vertices. And again, we'll go for a walk around the vertex. This time we'll go clockwise just to change things up. Okay, so here we go. We see those two vertices actually are the same. Okay, and then so is this one. And we see that we're going to keep going like this and never come back to where we started. It's never going to close up. And so that means that a neighborhood of that vertex is actually not a topological disk. And so we've made a mistake because whatever we've made is not a surface. So what we have to do is we have to remove that vertex, and we have to remove any vertices of like this, which we're going to call infinite degree vertices. And I mean vertices where infinitely many vertices have been identified together. So that's the recipe. That's the definition of a translation surface. We start with countably many finite Euclidean polygons. We identify pairs of parallel edges of equal length by translation, and then we remove vertices of infinite degree. There's two other equivalent definitions of a translation surface. The first one is a translation surface is a connected topological surface S, and a maximal translation atlas on S removes sigma. So we take away sigma, where sigma is a discrete set And every point in sigma is a conical point, like one of these points that we saw earlier. And the maximal translation atlas on S minus sigma is an atlas of charts on our surface, S minus sigma, where all the transition functions are translations. So you can even figure out from our constructive definition that we saw earlier with the polygons glued together how you would create this maximal atlas on S minus sigma. You could, start out by creating charts that are roughly based on the polygons. And then the transition maps would be the translations that we use to glue the polygons together. Another equivalent definition is the analytic definition, which is a translation surface is a pair x omega, where x is a connected Riemann surface and omega is a holomorphic one form, which is not identically zero. And again, just to give you a hint of how to relate it back to our definition with polygons, you can think of the Euclidean plane as the complex plane, so it has a complex structure on it, and that gives a complex structure on each of the polygons, right? And you can, like we talked just a moment ago, think about how you could make an atlas of charts based on the polygons. And then just consider dz on the complex plane. And that's going to induce a one form on all your polygons, which you pull back to the surface. And that will be your non-zero one form. So one of the first things we notice about translation surfaces is that they have singularities. So let's define what that is. Let x be a translation surface, and let x bar be its metric completion. Now take x bar and take away x. Those points are the singularities of x. And we can have many different types of singularities, and we're going to look at all the different types now. So let's say we had y in x bar minus x. Y is a regular singularity if we take a neighborhood of y in x bar and it's isometric to a Euclidean disk. So an example of that is when we looked at that surface with the infinite steps earlier. You can think of another translation surface, which is almost the same, except we remove this point here. In that translation surface, that point would still be in the metric completion, and so that would be a regular singularity, because a neighborhood of it would be, an epsilon neighborhood of it would be this ball here, which is exactly isometric to a Euclidean disk. If we look at all the different ways to linearly approach this singularity at unit speed, we see that we have a circle worth of ways, and we can measure that circle. The total angle is going to be 2 pi, and we measure just comparing to little angle sectors of Euclidean space. Okay, the second type of singularity is a conical singularity. So y is a conical singularity if there exists a locally isometric n-sheeted covering map from a deleted neighborhood of y in the metric completion to a deleted neighborhood of 0 in the Euclidean plane. So I've put a little picture of what that might look like here. Basically, it's a cone point where you have excess angle. So if you look at the space of linear approaches, the different ways you can approach that point along a straight line at unit speed, we still get a circle worth of ways to do it, but the measure of that circle is different. And again, we're measuring by comparing to sectors of Euclidean space. And we find that the total angle here is going to be n times 2 pi for some n bigger than 1. And just to clarify, what I mean by a deleted neighborhood is you take an epsilon neighborhood of the point and then you remove the point from that. Okay, the third type of singularity is an infinite angle singularity. So y is an infinite angle singularity if a deleted neighborhood of y in the metric completion x bar is isometric to the universal cover of a deleted neighborhood of 0 in R2. And so I've drawn a little picture of it here, but it spirals around like this forever and ever in both directions like this. And if we're measuring the angle that it sweeps out in the same way as we've been measuring previously, we'd find it has infinite angle. The final type of singularity is a wild singularity. A point y in the metric completion take away the translation surface is wild if it's none of the above. 1 to 3 do not hold. So I've drawn a cartoon of what one might look like here, but it's not, there's ways in which this picture is not accurate. A lot of crazy behaviors happen. In this picture, I'm just trying to show that you might have several connected components of linear approaches. And I've also included here number 5, if there's a point y in the surface itself that satisfies property 2, we also call it a conical singularity. And so whenever you're reading about translation surfaces or talking to someone about them, always clarify about, for yourself in your mind, about every conical singularity, whether they mean for it to be in the surface or whether it's not in the surface. Notice, though, that infinite angle singularities and wild singularities can never be points in the surface. You can never have points like that in the surface because their neighborhoods are not homeomorphic to a disk. That's it. There's regular singularities, conical singularities, infinite angle singularities, and wild singularities. If a surface has a wild singularity, then the translation surface is called wild. If it doesn't have a wild singularity, then it's called tame. Okay, so now let's talk about what it means for a translation surface to be of infinite type. It's a little bit different than a topological surface being of infinite type, so let's pay attention to the differences. A translation surface X is of finite type if the metric completion X bar is a compact closed surface and the singularities are discrete in X bar. Okay, and then X, the translation surface, is of infinite type if it is not of finite type. So notice that there's nothing about the fundamental group in the definition itself, and let's look at some examples to compare and contrast with the definition of topological surfaces of finite type. So the first example is, let's say I have a row of squares glued together in this way, and just the top and the bottom of each square is identified. So there's no vertices of infinite degree, and so once I'm done identifying all this, I get an infinite cylinder. There's no singularities. The metric completion is the translation surface itself. It is not a compact closed surface, and so this is not a finite type. It's of infinite type, and it doesn't have any singularities. And notice that the fundamental group is finitely generated here. Okay, let's look at a second example. So let's say we take this octagon and we identify opposite edges. Okay, so this is a translation surface of finite type. Its metric completion is itself, and it has one singularity, a conical singularity, which occurs at this vertex. All the vertices are identified together, and that's the conical singularity. Now I could think of a slightly different translation surface, which is the same as that, except I remove this point here. Okay, and then now to describe this translation surface in terms of polygons identified together, I would actually need infinitely many polygons just to get all the points as I approach that missing point. And so we see that finite type doesn't have to do with the number of polygons that you use either, because this surface is going to be a finite type. Why? Look at the metric completion. The metric completion is this surface over here, the octagon without any points removed. That is a compact closed surface. Its singularities are discrete. Okay, so this is a surface of finite type, even though we need infinitely many polygons to describe it. Our next example is the Baker's map surface. So we begin with a square, and we split the two horizontal edges of the square in half by adding a vertex. And then I continue to the right here, and I split that half in half, and then I split the quarter in half again, and then I continue like this to the left. And then I continue to the right in the same way by splitting in half and half again on the bottom edge. And then I identify these two, and then these two, and these two, and these two edges, and so on and so forth. And vertically, I do the same thing. I first split in half, and then I take the top half and glue it to the bottom half here. Take this quarter, glue it to this quarter. Take this eighth, glue it to this eighth. Glue this edge to this edge, so on and so forth. Okay, and the dotted lines are showing you our countable set of finite Euclidean polygons. And as before, we're going to investigate what is the metric completion. We're going to look at what is a neighborhood of one of these vertices. So let's start with this vertex here. And let's take a walk around the vertex in this direction. Okay, so if I go like this, I'll come out over here, and then over here in this direction, and then over here in this direction, and then over here in this direction. So I see I'm getting sort of every other. Okay, and then let's look at the other vertex, which I'll do in blue. And it's sort of, as we walk around, we see we're getting a neighborhood of the remaining vertices along the boundary of this big square. So we might think from this that we have two singularities that are each infinite angle singularities. But what's the distance between the two? Is it that? Is it that? Is it that? Oh, actually the distance is 0, right? We can find smaller and smaller paths between the two singularities. So what we have here is one wild singularity. The surface is of infinite type. You can see one handle here, and another handle here, and so on and so forth. And so its metric completion has infinite genus, it has the one wild singularity, and this is the Baker's map surface. So what we're thinking is an infinite type translation surface means maybe it's infinite type topology, but it could also be that there's infinite area or infinitely many singularities. All of this can be going on in an infinite type translation surface. So what can we do with a translation surface? Well, one thing we can do is apply affine linear maps. So if you have your collection of polygons here with identifications, and then let's say we apply to that some linear transformation. Okay, and I'm thinking these polygons are somewhere in the plane, and I just apply this transformation to the whole plane, and I see what happens to my polygons. All right, so they get all shifted like this in some linear way, and the identifications stay the same. So this is still identified to this, and this is still identified to this, you know, and so on and so forth. And we get another translation surface. And so we can move around in the space of translation surfaces by applying linear maps. And sometimes you can get back the same translation surface. Okay, and so like a very simple example of that is we start with this translation surface, which is the torus, no singularities, and I apply this linear map to the torus, and what that does is it shears it in this way. Okay, and then let's say I cut along this line here, and then I take this piece, and I notice this edge is identified to this edge. So I'm going to take this piece and translate it over here, and then I find that when I cut, translate, paste, I get this representation of the output translation surface. And this is exactly the same as this. We've gotten a square back with the tops identified and the side edges identified by translation. The square is the same dimensions. These are the same translation surface. There's an isometric homeomorphism between them. So sometimes you get back the same translation surface. And so it's interesting then to look at what linear transformations fix your translation surface like this. So if X is a translation surface, we define gamma of X to be the subgroup of GL2R that stabilizes X. And that group is called the Veech group of X. Okay, and you might be thinking, why didn't I put SL to R instead? Because, I would want area to be preserved, right? So for finite type translation surfaces, yes, this would be SL to R. But because we're looking at infinite type translation surfaces, we just need it to be invertible. You can do some sort of, imagine like a Hilbert hotel trick where actually, you move over the area like this and you get back to the same translation surface even though your linear transformation doesn't preserve area. A natural question to ask then would be, what groups are Veech groups for some translation surface? And so I've summarized the results of research in this area. So if you have a group that is at most countable, it is possible to find a translation structure on the Loch Ness Monster with that group as your Veech group. So this is a result of Pristiki, Schmidtushin, and Valdez. I'm sorry for the pronunciation. If you have a group that is countable without contracting elements, so by contracting elements we mean matrices that if I take powers of that matrix again and again, I don't get a sequence that's limiting to the zero matrix. As long as I don't have matrices like that, it's possible to find a tame Loch Ness Monster. That means a Loch Ness Monster with a translation structure that has no wild singularities, with this group as its Veech group. Okay, and this is the same group of people found this. Now suppose you have the same type of group, countable with no contracting elements. It's also possible to find a tame blooming Cantor tree with a translation structure for which this is the Veech group. And this is a result of Ramirez and Valdez in 2016. Okay, another thing that people study is the relationship between Veech groups and coverings of translation surfaces. So you can think of covering spaces, topological covering spaces, where both the covering space and the base space have translation structures, and the covering map respects these translation structures. And then you might ask, what is the relationship between the Veech group of the base and the Veech group of the cover? So one example of work in this direction, but there is much more, is that of Hooper and Weiss, and they looked at Veech groups of Z covers of square-tiled translation surfaces of genus 2. Okay, another direction for research, each Veech group element determines an element of the mapping class group of the underlying surface, right? And so we can use the tools of translation surfaces to study the mapping class group of surfaces of infinite type. So there is a Thurston-Veech construction of translation surfaces of finite type with many pseudo-Anosov transformations in the Veech group, so it will have very interesting dynamics. In 2015, Pat Hooper extended this idea to surfaces of infinite type, and so he's able to find specific translation structures on these surfaces that have certain elements in their Veech groups. And in this conference itself, Israel Morales will be talking about using this construction to find loxodromic elements in big mapping class groups, so you should definitely check out his talk. Another thing you can do on a translation surface is look at the translation flow. So let's say you have a translation surface, and here's all the polygons with their identifications. You pick a direction and you pick a point on your translation surface, and it makes sense to travel in that direction at unit speed, and you just travel along until you hit an edge, and then you follow the edge identifications to know where you should travel next. And because the polygons are identified together using translations, and translations don't change the direction of a vector, this flow is well defined for most points and most times. The only situation where it wouldn't be well defined is if a point flows into a singularity. Then it's not clear how to continue from there. So this flow isn't defined for all points and all times, but there's still some interesting dynamics going on. So people study what directions have periodic trajectories, what directions have recurrent trajectories, what directions are ergodic. It's also interesting to take a transversal to the translation flow, take a point on the transversal, flow it, see where does it come back. And this gives a map from the transversal to itself that we call an interval exchange transformation. And by studying translation surfaces of infinite type, we get to study infinite interval exchange transformations. So here's a quick list of examples of infinite type translation surfaces where people have studied these questions. The infinite step billiard is the first example of a translation surface we saw in this talk. So it's important to note that while I showed translation flow and Veech group as two separate things, they're incredibly related and it's impossible to study one without studying the other. I'm going to end by telling you the definition of a half translation surface because it's often studied in the same fell swoop as translation surfaces. So they're almost the same as translation surfaces. We begin with a countable set of finite Euclidean polygons. Every edge is identified to another edge that's of equal length and parallel, not by translation, but by translation and possibly rotation by pi. Looking at the geometric definition, a translation surface is a connected topological surface X and a maximal half translation atlas. So that means the transition functions can be translations or translations composed with rotation by pi. For the analytic definition, a translation surface is a pair X omega, where X is a connected Riemann surface and omega is a holomorphic quadratic differential. So half translation surfaces also have Veech groups, and people also study the dynamics of trajectories on them, and it is interesting to look at half translation surfaces of infinite type. With that, I want to thank you for listening to my talk and encourage you to check out Israel Morales' talk. Thanks.